Recording is rolling. It is Thursday, October 3rd. So I want to take one more day this week to focus on puzzles, give you guys some time in class. Last few days we've been looking at these. So mostly I've been referring to the solutions that are posted, showing you guys how to set these up and think about them. I want to do something a little bit more guided today, walk through at least a couple of these up here, and hopefully we'll have some class time. Also let you guys work a little bit more independently also, and then I can walk around, troubleshoot any questions you guys have. I want to get you guys this take-home quiz by the end of class today, and then you guys have a few days to do it. And so all this stuff can be due Monday. But you know, if you finish anything early, feel free to turn stuff in early. Turn something in tomorrow if you finish it early. It's all right too. All right, so plan tomorrow is have a FRQ queued up, so that'll be our focus tomorrow. You guys know this PSAT is coming up on Wednesday coming up. Right, so I was looking at I have a list of all the students in the school who are taking it. I was trying to find my own students. So this is mostly 10th graders, I think. Oh, yeah. Huh? Does anybody know when the SAT is? Well, okay, the PSAT is in the school coming up Wednesday. When is the I don't know about the SAT. I don't know. It's this week. Okay. Yeah, I don't know. Okay. Yeah, there could be independent SATs off campus. Is there going to be one on campus by the school? Maybe. I don't know anything about that though. Right. And then guys, here's what's going on for us. If you're in 10th grade, I did look you up and I gave you guys a sticky note where you're going to be testing. If you think maybe if you're in 11th grade, you think you might be taking it because there are a few, let me know. I can look you up on the list and see if you're on the list. Oh, now this particular classroom is going to be used for testing. But I'm not going to be a proctor. Someone else is going to be here. So they're relocating all my classes to the media center. So if you're not testing, where are you going to show up on Wednesday? Media center. Okay, and we're going to be in the media center all day. Okay, or I am. Oh yeah. Okay. You think you're taking it? Okay. So hold on to that, and I'll look you up closer to the end of the class. Okay. I'll see if you take it then. Huh? Let me see. Actually, let me pause this real fast. I'll look at real fast too. All right, back here then. So, you guys have these chapter puzzles. We had gone over, a big picture view how to solve these. One of them I want to walk you guys through today is, let's look at this bird feeder. Do you guys see number 19 bird feeder? Right. Maybe you've solved this one on paper yet, maybe not. If you have and you feel comfortable with this, just go ahead and you can work independently on something. But here, everybody, I'm going to walk you guys through. We've got 150 Newton bird feeder, and it's held by these cables at 60 degrees, 30 degrees from the horizontal. So what is the tension in each cable? Of course, you guys have the solutions post these, but one of the reasons I wanted this is the solutions I wasn't able to fit on one page. It looks a little bit crammed. It's like I guess one thing I could do is just draw this a lot bigger. So I guess a little bit nicer looking notes here. Okay. So I got this dot where these strings come together, and I'm going to analyze this in terms of components. So we dash off some axes, got like an XY axis system. Got it? Okay. And here's the point where all the strings come together. I got a bird feeder that's hanging straight down. Here, maybe I'll use pink ink for my forces just to make them stand out a little bit better. Okay. And that was 150 newtons. So, well, I'll say mg equals 150 newtons. Right. Or I should have asked you guys, when they say 150 Newton bird feeder, look at you guys right now. 150 Newton bird feeder, is that referring to a mass or a weight? A weight, because it's measured in newtons. Right? Guys, what would the mass of this bird feeder be? 15 kilograms, right? Which we're not going to actually use for this question, but if it was in motion, you had to do Newton's second law of motion, something, you might want to know that. Okay? If you had a textbook that said the bird feeder has a mass of 15 kilograms, you'd want to immediately convert that to a weight, 150 newtons, so that you could get this central force that way. All right, there's also, let's see, rope pulling up to the left at a pretty steep angle, trying to always proportionally correctly, pretty close. Okay? And then one at 90 degrees to that, because it's shallow angle about this way. All right. Okay. I'm trying to draw these so they're pretty close to scale. Okay. Can you guys draw that on your paper? Okay. I'm going to label this one tension left, this one tension right. Okay. Okay. But we're gonna just go ahead and use exactly the numbers that they provided. So they were saying, if you look at their picture here, this angle in the top left is 60 degrees, and this angle in the top right is 30 degrees. Could that also be this angle and this angle respectively? Could that also represent, this could be 60 degrees and this could be 30 degrees? Kind of translate that around, right? Do some geometry. Right, same thing. Okay, guys, if you just completely correctly to scale, it should look really, really close to mine. Do you guys see how, guys, if there's 60 degrees here and 30 degrees here, do you guys think there's a 90-degree angle between those two strings? That is not be relevant. I'm just thinking geometrically what that should look like. Can help you out a bit. Okay. Now, you guys know part of this is we're going to break these vectors into components. Now, we don't know what the two tensions are. So they'll show up as unknown values in a system of equations is where this is headed. But this one's kind of pulling to the left. This one's kind of pulling to the right. And they're both pulling kind of up to balance out the weight that's pulling straight down. So did you guys also dash your components like I did? We put little arrowheads on these. Left, up, right, up. You guys see that? Okay. Let's got that. Okay. So we see something like this. Someone's hanging from some strings or some ropes. Okay, you want to figure out what's the tension on each side. Okay. This is a really classic physics setup. If you see a giant structure, maybe a truss bridge or something, there could be a compression version of this. This is tension, you got a compression. It'd be a similar geometry, similar approach to what we're doing right now. Okay. Right. Now, again, if you drew this absolutely correctly, do you guys see this one's pulling right as much as this one's pulling left? You guys see these two cancel out, right and left? Okay. And see this one's pulling a lot up, this one's pulling a little up. But if you add those two bits together, this is so many units up, so many units up. Should that exactly cancel out the 150 newtons down? You see it? So if you're looking for a poster that'll tell you exactly set up, it's really this right here. This is what we're doing. Okay. So asymmetrical joint and tension, right, left cancel, up and down cancel. All right, let's get some magnitudes here. Let's start with this one right here. Guys, this component I can call equal to what times what? Ah, there you go. Take your full left tension, which we still don't know what it is, multiply by exactly sine of 60 degrees. Okay, that's what that is. Hey, does anybody know as a ratio what is sine of 60 degrees? So here, it's like √3/2. Let me show you guys that's true. Sine of 60 degrees is 0.866. You guys see that? What is the √3/2? Hey, it's the same thing, 0.866. You guys see that? It's one of those little good things to know. It might show up quite a bit, right? 30, 60, 90 triangles are common. I could call it equal to √3/2 times tension left as a fraction. So pick your favorite. You could do the decimal if you want. If you want to do 0.866 times tension left, you could do that also. Okay. How about this bit right here? What is this one equal to? Ah, tension left times cosine of 60 degrees. Hey guys, what is cosine of 60 degrees? 1/2 exactly. Okay, let's see if it is. What is cosine of 60 degrees? 0.5 exactly. Look at that. 0.5 exactly. That's it. So let me turn this thing off. Hang on. Might make a loud noise. There you go. All right. I think I'm gonna bring in a different amp. Try that. All right. So could that be equal to just half of whatever the left tension happens to be? All right, which we're gonna solve. Okay, so we got that. How about this bit right here? Is that tension right cosine 30 degrees? Tension right times cosine 30 degrees. What's cosine of 30 degrees? Could be √3/2. So that's √3/2 times tension right. So forth. And then you guys think this one's tension right times sine of 30 degrees? Guys, what is sine of 30 degrees? 0.5. So that's equal to 1/2 of tension right. So, all right, there you go. Okay. So there's only one hard number we have in terms of force in newtons. That's the weight, 150 newtons. Here, maybe I'll circle the relevant numbers to set up an equation. Right, we've got the weight pulling down. We got √3/2 tension left pulling up. we got half of the right tension pulling up. Okay, so there's their vertical forces. And then horizontally, I got half of the left tension and √3/2 of the right tension that are canceling out along that axis. Okay. All right, that all right? Left and right cancel, up and down cancel. Okay. Everybody right? All right, so now we got to set up a system of equations. You guys ready for a system of equations? Okay, here we go. Maybe I'll even spell that out. System of equations. So let's do sum of forces in the x direction goes to 0 newtons. Okay, that's going to lead to this right minus this left goes to 0. Okay. So I can say √3/2 tension right minus 1/2 tension left zeroes out. Okay. You know, could I? Well, here I'll put that aside. We're going to come back to that. How about the other equation? Sum of forces in the y direction goes to 0. Well, now I have 3 forces in the y direction. Okay. Can you guys write this equation before I do? Or give you guys a little head start. Sometimes I think I go a little bit too fast, but see if you can write that before I do. You're getting it right, then you're on a good path. Okay. You guys do see the big overall framework of how we're solving this? Okay. Right, left cancel, up and down cancel. Right, we're just setting up the equation. We went through the geometry. Right. Right. So I'm thinking here, this one's pulled up, √3/2. Tension left is pulling up. Plus 1/2 tension right is also pulling up. So same direction. So they're adding together. Okay. Minus this 150 newtons. Newtons equals 0. Okay. Well, newtons. Something like that, right? These are all in newtons. Those are 2 force equations. Oh, there you go. There's your system right there. So that's 2 independent equations with the same 2 unknown variables. So does that mean at that point, in principle, this is solvable? Yep. Now pick your favorite algebra method to solve it. I know at least 3 different methods you could do. You could do substitution, you could do elimination, you could do matrices. I think I'm going to do, what do you guys feel like doing? Huh? I'm hearing substitution. Okay, let's do substitution. Okay, let's do that. Okay, so what I could do is I could take one of these equations, probably this first one, this x direction one, solve for one variable in terms of the other variable, and substitute that into the other equation. Sure, we did it. Okay, so let's take this top equation and rearrange this. So can I slide the 1/2 TL over? So √3/2 tension right equals 1/2 tension left. Right. Oh, and could I also multiply both sides by 2 and just get rid of that over 2 right there? Right, make it look like this. √3 tension right is equal to tension left. Okay, or something like that. Okay. That's all from that x direction formula. Okay. Now let's bring in the y direction formula and bring this in conjunction with that. And here's where I'll write the word substitution. Substitution. Right there. We're going to substitute this expression in for the left tension. I know the left tension is √3 times the right tension, so I can substitute that right there. Right? Isn't that whole expression going to just feed right into the left tension? Right? Right. So let's try that. So I got, see, √3/2 times the left tension, but I'm not going to write the left tension. I'm going to write this expression right here. √3 times the right tension. And then plus, okay, I have another right tension here, half right tension right, minus 150 newtons goes to 0. Right, there you go. All right, now that we did the substitution, we've got one equation with now one unknown quantity, which is the right tension. So we're about to get the right tension. All right, guys good so far? Okay. So while you guys are catching up to that point, recap what we've done so far. is all they told you was the weight of the bird feeder and the angles. Okay. So we split the diagonal forces into components. Now we don't know what they are yet, but we knew there's like some ratios floating around. We set up system of equations, x direction, y direction, everything zeroes out because equilibrium. We just did a substitution. And now we're about to just check through a little bit of algebra to get one of the tensions, the right tension. So they got it. Guys, what is the root 3 times the root 3? 3. So 3/2 of the right tension plus 1/2 of the right tension. Can I do this while I'm at it? Can I just slide over 150 and say equals 150 newtons? That's all right, right? All right, all good. All right. Put this together. Is that see, 4/2 gotta be 2 times the right tension. 2 times the right tension is 150 newtons, right? Okay. All right. And then last step is divided by 2. The right tension must be 75 newtons. It's a continue here. All right. Therefore, tension right equals 75 newtons. Okay. All right. Let's check it out. You guys all right? All right. Right. Now that we know what the right tension is, we can get the left tension really fast because we can really use any of the above, anything on this paper, right? But I think the fastest way is, guys, look at this expression right here. You guys remember this? I dash outlined this because I use this as a substitution term, right? We can get the left tension right away because I'm just going to bring that back in. Remember from before that the left tension was the root 3 times the right tension? That's from before. Bring that right there. Okay. Now all you got to do is substitute in the right tension, which is now a known value, root 3 times that. So the left tension, therefore, must be, say, what is the square root of 3? And then close parenthesis times 75 newtons. This looks like 129.9 newtons. There you go. All right. Those are the two tensions. All right. Is that right? Yeah. All right. And again, answer in physics, good to say, does that make sense? Maybe check your work. Okay, let's take, now you guys know the answers to left and right tensions. Okay, let's take these values, look back at the original diagram. See if I can fit this all on one screen here. Maybe. I think that kind of fits pretty close if I zoom out of it. Okay, it just fits about. Okay. See, does this work? All right, so let's try the vertical. If I do root 3 close parenthesis on 2 times the left tension, I'm calling 129.9 plus 1/2 of the right tension, which said was 75 newtons. Right. This should add, guys, what should this plus this add up to? 150. All right, to cancel down with this one. Let's say if it's about 150. 149.996. Yeah, that's 150. Right? 150. Right. And how about this right and left? Should zero out. Let's see if that's also true. Root 3 close parenthesis on 2 times the right tension was 75 newtons minus 1/2 of the left tension, which is 129.9. Let's see if this is really close to zero, maybe tiny number. Let's see if it is 0.0019. Yeah, that's 0 newtons. Okay. This is 129.9, is a tiny bit rounded. All right, it worked. It worked. All right, you guys good on the bird feeder? Hopefully so. And hey, if you need more practice, I mean, that's what you got the homework puzzles for. You guys got a few more days to look at those if you like. Right, so I want to do at least one more guided type practice with you guys that signed. Let's do one of these Atwoods. All right, now I got a modified and I got a double elevator. But did I also assign a fancy one? That was like, oh yeah, okay. There's also number 28. Did we do 28 in class? Yeah, we did, or something like that. So here, you guys tell me. I got number 28, the incline Atwood. Number 36 modified and number 38 classic Atwood. Which one do you guys want to do in class right now? The hardest one? that sound like number 28, the incline? Okay, I think we did a similar type 1 in class, but not actually this particular one, I think. Okay, yeah, I think number 28 kind of, if you can do this one, you can definitely do the other ones. All right. All right, so we got 2 packing crates. Got 5 versus 10 kilograms over like string. Okay, so the string itself does tiny mass compared to the weights, the crates. Well, smooth incline at 40 degrees. Guys, you guys see that word smooth? Yeah, there you go. No friction. That's not really how friction works, but it's just one of those words that's kind of stuck around as a kind of a keyword in physics for no friction. Okay. Find what's the acceleration of the crate and the tension of the string. There you go. Notice they're specifying one of the crates for the acceleration. I think it's so you can also apply a direction to it, but you know that the magnitude of acceleration is going to be the same for both of them. There you go, 28. All right, so we got this inclined outward. Now 40 degrees, that's pretty steep. I mean, it's a little bit less than 45 degrees. All right, we draw an incline, big old incline right there. There's the incline. Let's get a couple of crates going. So this guy is 10 kilograms. This guy up here, 5 kilograms. Got center mass. Right. A pulley right here, and some string going. String. All right. 40 degrees. Let me throw in 40 degrees. Okay, I think that's the whole setup right there, and there's no friction. So maybe I'll even specify that. No friction. No friction anywhere, especially between that small block on the surface. All right, let's get some forces. Oh, guys, what's the what do you want to use for the weight of the 10 kilogram guy? 100 newtons? Let's do 100 newtons. I think in the solutions I did 98 newtons, but yeah, let's throw the notes. Just go ahead and do 100 newtons. The answer won't be a whole lot different anyway. Right. If that weighs 100 newtons, how much does the 5 kilogram guy weigh? 50 newtons. Now, guys, if you draw this to scale, how long should I draw this vector compared to this vector? Aha. Yeah, that exactly. It's about 8 centimeters long. I guess this guy should be about 4 centimeters long. If I do it right. Pretty close. All right. So yeah, 50 newtons. There you go. Okay. Right. Oh, you guys think there's a tension in the string? Because the tension's probably between what and what about? 100. You know what? Actually, it might possibly be less than 50. It's definitely less than 100 though, right? Right. So I don't know what the tension is, but I know it's less than 100 newtons. Here, I'm just going to draw some. I know it has to be larger than 50 sine 40 degrees. I'll show you guys why here in a minute. Here, I'm thinking ahead a little bit. Sine 40, which is 32 newtons. It's somewhere between 32 newtons and 100 newtons. So I'm going to draw it as, how about, I'll make it kind of close to 50-ish newtons. I don't know what it is yet. Tension force. That's one of the questions anyway. Right. Guys, should it be the same tension on both blocks? Yeah, same tension on both blocks. Right. As long as this pulley is massless, frictionless, that should be the case. It's usually the case in this class. All right, we're good so far. Okay. Now, for an incline, guys, anytime you see an incline, I should introduce what kind of system? A rotated Cartesian system. Right, so that's aligned with the surface. Yeah, Cartesian system. There you go. You guys think Cartesian system. So let's go parallel to the surface and perpendicular to the surface through that center mass of the 5 kilogram block. Right? Because we need some forces and some force components that align with that. That true? Okay. All right, so let's go. Let's break this 50 Newton weight into components. That weight is partly pushing the block into the incline and partly trying to drag it down and to the right, parallel to the incline. You guys see how I'm holding my ruler right now, parallel to the surface? Guys, am I holding my ruler parallel to the ground? No. Parallel to the surface. You guys are doing parallel to the surface? All right, so parallel to the surface. And then again, some component of the weight's pulling that way. We throw in, guys, what is this angle right here? 40 degrees. Oh yeah, 40 degrees. Okay. Now if that's 40 degrees, then what is this component right here equal to? Aha, 50 newtons times sine of 40 degrees. Let's go ahead and get a hard number for that. I think that'll just be easier. What's 50 newtons sine 40 degrees? I'm getting 32.14 newtons. Let's go 32.14 newtons. Okay. Okay. All right. And I guess this would be the cosine component over here. So I'll say equals 50 newtons times cosine, 40 degrees. We go get a hard number for that. Scroll up, scroll over, pop in a cosine, 38.30 newtons. 38.30 newtons. There you go. So now we got the two components. Okay. Am I finished drawing forces, or do I still need another force? Which one? Normal force. Guys, are you guys gonna draw? The normal force goes straight up against gravity. Does it do that? No. What does normal mean? Perpendicular? Perpendicular to the surface? You guys draw perpendicular to the surface? How long? Guys, what's the magnitude of this normal force vector? How many newtons? Yeah, 58 cosine 40 degrees is 38.30 newtons. All right. Now, I think this particular setup that ends up being irrelevant, like if you forgot that, it's not going to change the mathematical answer. Okay. But guys, what if there was, here's why, it's perpendicular to the surface. It's not going to drive the motion along the surface, right? Parallel, right? But what if there was friction? Guys, if there was friction, would it be important to have gotten the normal force? Yeah, because what do you know about friction force and normal force? What's the relationship? Coefficient of friction times normal force, right? Like that. You guys remember that? Right. So if there was friction, okay, at this point we know what the normal force is. If you were told the coefficient of friction, you could solve for the friction force. And that was, I think that was one we did yesterday. Okay, it's in your notes from yesterday. We did something like that. Right? Could you do the other way? Like, what if, what if, for example, you had, we're given like, oh, they're in equilibrium. Maybe they're sliding at constant velocity. Could slide at constant velocity to equilibrium, which would mean zero net force, which means maybe you could calculate what the necessary friction force would be. And could you get a question like, what coefficient of friction would make that possible? Could you do it that way too? It'll be a little bit backwards, but I bet you could do that. Right? You guys think? Right. Just think about possibilities there. Right? But I think we have like an air hockey table. So let's go and circle all the relevant forces that are driving the motion. Oh, you guys probably figured, I should have asked you guys like 5 minutes ago. Guys, which way is this going to be moving? Probably clockwise or counterclockwise? Probably counterclockwise, right? That's, by the way, why I was guessing this tension force would be more than 32 newtons. Remember I said that? That's why. And again, if there was friction, it'd be really, really important that you guess the correct direction, because the friction force should be opposing that. Right? But the fact that there's no friction, you don't even have to guess what direction, because the math is just going to play out however. Okay? Right. Let's go through circle the relevant driving force. Let's do a whole system approach. Right? You could do a system of equations, that block and that block, or you could look at the whole system. Let's do the whole system. I usually just do it that way anyway. Right? So guys, which are the net external forces or force components that are going to drive the whole system? What's one of them? The what? Yeah. This one right here. Yeah, this one right here. You want circles. This 32. Okay, yeah. 32.14 newton force right there. Right. It's trying to make the whole system go. Well, I'll call it clockwise. Okay. What else matters? 100 newtons. The weight of this guy pulling it back counterclockwise. Isn't that true? Okay. Now today those are the only ones that matter, because okay, this normal force just cancels out this component of the way that's not driving the motion either way. The tension force is just internal to the two block system. So from a whole system approach, I can ignore anything that's internal. Right. Now yesterday I did throw in friction, so I circled one more because there was friction. But today we just got those two. Okay. All right, all good? All right, let's do equation time. Oh, guys, what equation should I set up next to solve for the acceleration? Newton's second law. Newton's second law. All right, so Newton's second law, the acceleration is the net force on the total mass. Okay. Net force. Here, give you guys a minute. So you guys stay a step ahead of me. You guys got that so far? Okay, go throw this diagram back up here. Give you guys a head start. Fill in that equation before I do. What is that equation exactly going to look like? I set up what's a fraction bar. I said acceleration equals, and I set up a fraction bar for you guys. Right, what goes in the numerator, what goes in the denominator? And again, we're doing a whole system approach. So I'm looking at the 2-block system as a giant system that's just all strung together. All right, you guys figure out the equation? All right. So again, we're doing second law for the whole 2-block system. All right. So what is the net force driving the system? What do you guys say? That sounds about right. About 67 something. Do you do 100 minus 32? Right. Yeah. So 100 newtons. Saying let's go counterclockwise minus the 32.14 newtons. Say no, let's go clockwise. There's your net force. You guys got 67 point something newtons. Right. How much total mass is being moved around? 15 kilograms. That's right. Got 10 kg there. Got another 5 kg there. The connecting rope itself is negligible. Okay. All right, let's get what's the acceleration? So 100 minus 38.14 on okay. Whoops. 4.12. Okay, I mean meters per second squared. Okay, so that's the magnitude of acceleration. If you were to focus on one block, you could also apply a direction. You say that's the so for the 10 kilogram block that would be down, or for the 5 kilogram block that could be up and to the left at 40 degrees above the horizontal. If you had to apply a direction, right? Because acceleration could be you can think like a vector, right? As a direction too. All right, guys, good. Good. There was another question. It says, what is the tension in the string? You guys ready to get tension in the string? Okay. No, tension in the string. How do you figure that out? Okay, yeah, it is Newton's second law. Yep, Newton's second law. Except instead of focusing on the 2-block entire system, should I just focus on a single block? Right? Can I pick either block and it's going to tell me the same tension? Right? Here, let's do it this way. Let's just pick one of them. We'll solve it, and then we'll take a look at the other block and see if it actually checks out. All right, we'll do the other as a check. Guys, which block do you think is probably a little bit easier to solve the tension with? Yeah, probably the one that's hanging straight down, straight up. Got less going on with it. So let's do that one. Let's do Newton's second law of motion just for that block. So I'll do F net equals mass times acceleration. Okay. Now, what is the net force? How are you guys going to draw the net force for that 10 kilogram block? Yeah, it's the difference between these two. Yeah. Oh, true. Yeah. I guess if down is positive, it's accelerating that way anyway. Let's do 100 minus the tension force. So I like that idea. 100 newtons minus the mystery tension force results in a 10 kilogram block, 10 kg, accelerating straight down at how much? Yeah, 4.12 meters per second squared. I think there was like a little digit here. I'll throw an extra digit in there. I think that was on my calculator screen. Okay. All right. So can I add this over, subtract that over, get the tension force? Just a little algebra shuffle right here. It's 100 minus 10 times 4.124. I'm looking at 58.76 newtons. Okay. That's probably too much precision. Maybe we could say about 59 newtons. Okay. Yeah. But it's about 59 newtons, right? Okay. AP physics is not really a super stickler on significant digits. I think AP chemistry is. They're really strict about that, but AP physics, they're pretty loose about that. So for something like that, they would take it. Okay. All right, guys, good? All right. And the last thing I'm going to do with this one is take this tension force that we now solve. I want to run a check with the 5 kilogram block, say, does this actually work? Here's the way I'm going to do this. I'll do Newton's second law of motion as it applies to the other block and see if it gives the same acceleration that we already know what the acceleration is. Right? So let's take this tension force. Now we know this tension force is about 58 point something newtons. So let's do 58.76 newtons. That's that tension force that way. Right? Now to get the net force on this 5 kilogram block, okay, I've got this on my screen. What should I do next? Yeah, subtract out the 32 newtons here. So minus 32.14 newtons. Okay, there's my net force. Let me insert parentheses, group this all together. I should have started with open parentheses. Okay, now I got that in parentheses. I just did that minus that. You guys got that? Okay. Now, if I divide by the mass of the block, which is 5 kilograms, notice I just did net force divided by that mass, right? Guys, if we did this correctly, when I hit enter, what number has to pop up on the screen? Huh? 4.12, right? Because isn't this net force divided by this mass, doesn't that represent the acceleration of this block in this direction? Right? Which we already know what it is. It better be 4.12 meters per second squared, right? Guess yeah? All right, so we're doing a check here. Let's see if it is. Moment of truth. Ooh, something wrong. 32. Did we mess up? Did I get the acceleration wrong? Oh, you guys got 4.5? Whoa, did I plug this in wrong? All right, let's go fix that real fast. 100 minus 32.14 over 15. Wow, what the heck? Okay, there's a, oh, okay, misread that. Okay, 5. All right, let's do that real fast. All right, we can go fix this. So, 100 minus 10 times 4.524. Right. Yeah, good thing we did that check, right? So 54.76 newtons is the actual tension force you should be, right? It's a little bit less. All right. Now let's take that, and I'm gonna run my same check. So I got tension force here is that right? Okay. So this should actually be 54 newtons, 54.76 newtons. Subtract off the 32.14 newtons. Close that. Okay, so I got that in parentheses. There's the net force divided by 5 kilogram mass. Okay. All right. Let's see if this goes. Okay. When I hit enter again, what number should pop up on my screen now? Yeah, it better be this 4.52. Now, okay. So is this right? Let's see if it is. Okay. We're good. All right. Checks out. All right. You guys good there? Good. All right. So yeah, good. We have 10 minutes left in class. If you guys have any specific questions, let me know. And I'll give you guys some time to work independently. Also, I need to get you guys your take-home quiz. About to do right here. We get you guys your take-home quiz. And with that, let me wrap up this recording.